So finally, we are headed towards proving Urysohn's metrization theorem. So let's begin with some definitions. Right. So topological space X is said to be second countable if it has a basis B whose cardinality is countable. Okay, yeah. So Rn is second countable because we can take open subsets of the type balls A of radius epsilon, where epsilon belongs to rationals and this vector A belongs to Qn, right. So this forms a basis, and this is going to be a countable collection. So therefore Rn is second countable, and if X is second countable, then every subspace of X is second countable. Right. Okay. So next, let's define a regular space So topological space X is said to be regular if given a point X and a closed subspace A, then there exist open sets U and V such that X is in U, A is contained in V, and U intersection V is disjoint. Right. So earlier we had seen the example of normal topological spaces. So regular is weaker than normal, and obviously every normal topological space is regular. So what we need is, given a point X and this closed subspace A, we should be able to find a neighborhood around X and a neighborhood around A which are disjoint. Okay. So obviously normal implies regular. Okay. And for normal subspaces we had proved the following lemma. We had proved a lemma similar to the following one. So analogous, a similar proof. Okay, let me just write the statement first. Let X be a regular space and let X in U, where U is open. Right. So then we can find an open subset V such that X is in V, which is contained in V closure, which is contained in U. Right. So what do we have? We have a point X over here, and we have an open subset U. So then we can find a smaller neighborhood of X, which is V, such that the closure of V is completely contained inside U. Right. And the proof, we had proved a similar lemma for normal spaces. Right. So there, instead of X, we had a closed subset A. We had a closed subset A and an open set U, which contained A. So imitate that proof. The proof there. Okay. So the main theorem we want to prove is the following. The main theorem of this lecture: a regular and second countable space is normal. Okay, so let us prove this. Right. So let B denote a countable basis for X. So let's say our space is X, right? So X is second countable, so that means by definition X has a basis whose cardinality is countable, right? So let C and D be two disjoint closed subsets. Right. So we need to find open sets U and V such that C is contained in U, D is contained in V, and U intersection V is empty. Okay. So first we do this as follows: fix for X in D, not fix, sorry. Using the lemma, we can find an open set V such that X belongs to V, V is contained in V closure, and V closure is contained in X minus C, right? So D is contained in X minus C since C and D are disjoint, right? So our picture is something like this. We have two disjoint open subsets C and this is D, right? So D is contained in the complement of C, which is this, right? So we just choose any X in D and we can find a neighborhood V such that its closure is also contained in X minus C. This is using the lemma. Okay, so clearly we are allowed to shrink V if necessary, yeah. So thus replacing V by a smaller basic open subset, we may assume. So we have a basis for our topology, and that V is in P. right? X is in V, so that means that there is a basic open subset which contains, so X is in V, so there is a basic open subset which contains X and is completely contained inside V. Yeah. So therefore, we can replace our V by a smaller basic open subset which contains X, and the same condition will hold. Okay. So we can do this for each X in D, right? So for every X, so what have we done? So for every X, we get a basic open set V sub X such that, so this is in B, such that V sub X closure does not meet C. Okay. So since B is countable, we may enumerate this collection Vx. Or right, so we can just number these. This is a subset of a countable set, and therefore this has countable cardinality. So we can just say this V n's for n greater than or equal to 1, right? So now define Wn to be equal to the union I equal to 1 to n Vi's, right? So then what do we have? We have this W1 is a subset of W2 and so on. It's an increasing chain of open subsets. D is contained in the union of these Wi's, right? This is because as every X in D is in some Vi, right? And the third condition is that Wn closure is equal to union I equal to 1 to n Vi closure, sorry, Wn closure intersection C. Now there is a finite union, and therefore the closure will go inside Vi closure intersected C, and each Vi closure intersected C is empty, so this is empty, right? So we can do the same for points of C. So in the above, we were doing this for points of D, so we can do this for points of C. We get, once again, this increasing chain of open subsets. C is contained in the union of these, and 3, Un closure intersected with D is empty. Okay. Okay. So note that this implies that D is contained in X minus Un closure, right? So this implies that when we intersect both sides with W, we get Wn intersected D is contained in Wn minus Un closure, right? So this implies that the union Wn intersected D is contained in the union Wn minus Un closure. Now Wn is open and Un closure is closed, so when we look at Wn minus Un closure, this is an open subset, right? And this union is equal to union n greater than or equal to 1 Wn intersected with D, but as D is contained in this union, there is going to be equal to D, right? So thus we get D is contained in the union of this open sets, and similarly C will be contained in the union of Un minus Wn closure. Okay. So we claim that these are the required open subsets. Yeah. So we just have to show that the intersection is empty. So we claim that the intersection is empty, right? If not, there exists I comma j such that Wi intersected with Uj is not empty, right? So let us assume that, first assume that I is greater than or equal to j, right? Wi, Wj is contained in Wi and Uj is contained in Ui, right? So if we take an x in the intersection, this intersection right, so this implies that x is in Uj, but x does not belong to Ui closure, right? But this implies that x is in Uj, but and x does not belong to Ui, yeah, which is a contradiction. Right. So similarly, if j is greater than or equal to I, then we will have Wi is contained in Wj. So which will imply that x belongs to Wi, and so this will imply that x does not belong to Wj closure, x, that is x is in Wi and x does not belong to Wj, which is a contradiction. Right. So thus the intersection is empty. So this completes the proof of the theorem. So we will end this lecture here.